Okay, hey guys, this is going to be an example of the virtual work method. I'm just going to use the last example, or the last problem in the last homework, because I feel like that was a pretty interesting problem. There were some things in this problem that probably were not expected, specifically regarding the reactions. And so I am going to actually skip over some things, because I think that will cause more confusion than expected. Anyway, just as a note, I don't always get a chance to make corrections to these videos, so sometimes errors creep in, and I don't want them to. I never want errors to creep in, but but yeah, just keep that in mind when you're watching these. That I'm not infallible. I make plenty of mistakes, and yeah, if you feel like something's wrong in the video, or you feel like something I didn't include all the steps, or if I need to add something, then just shoot me an email and I'll check and I'll try and adjust things. Usually, yeah, no, usually I had to make a correction. Anyway, back onto topic. So our problem was, I'm not going to go into how to get your moment and shear diagrams for this, or just your moment diagrams. You don't really need your shear diagrams, but this problem was interesting because of finding the deflection at A. Your reaction was probably not what was expected. So let me just put this here, put this here. You had 50 and you had 10 going this way, and the question was this A, B, C, D, find delta AX and delta CX, I believe. Okay, so there were, first things first, you always find your reactions. We can agree, I think, that HD is gonna, DX is gonna be 10. And you have to use some, if we do moment about, let's do moment about D. We have 10 times, what is this like, 10 times 4? I think it's 4. Plus 50 times 4 equals 7A1. And we should get AY equals 35 point something. 34.3. And we should get dy equals 15.7. And like I said earlier, I'm not going to derive your moment equations, but you should end up getting, well, okay, so I'll walk you through your moment equations. Let's draw these. This is your P system. This is 15.7, this is 10. Okay, so as I go from here to here, or let's see, do you agree that I can break this up into an axial component and a shear component, and that the magnitude, right, because my force is a vector, and I can split my vector into two components. You can imagine, for example, that I'm turning this sideways, and this is my x direction, my y direction, and this is some diagonal. Well, if I just rotate this a little bit, rotate this back to my original frame, then yeah, I don't really know a better way of explaining that, but so the solution goes into the details of how to get this. Essentially, this is when I draw my triangles. This is going to be 5, 4, 3, And this component, my shear component of the shear component that my horizontal reaction causes in the diagonal member is going to be 34.3 times 3/5. So my moment diagram here is going to be triangular because I have a single force acting this way. And that force is just a function of x. So right, I have this, my moment diagram is going to be 34.3 times 3/5 x. And you can worry about the sign. I believe this is going to be, yeah, well, the sign doesn't end up mattering in this case. But 34.3 times 3/5 x, and then if I multiply this by 5, because I'm going along this way, I'm going to get the maximum moment. So I start off at 0, and then when m, so m of 0 equals 0. M of 5 is going to be 102.8. So let me use a different color. This will be 102.8. And then my moment about this corner has to be the same. So this is also going to be 102.8. So this is 102.8. This is also 102.8. This is just because it's a rigid frame, and the frame moments are continuous about the joints. Now let's look over at this side. This side I only have a force of 10. I only have a shear force of 10 here. So my moment equation is going to be in this arm equals 10x. So m of 0 is going to be 0 again, which is what you would expect, right? You expect it to be 0 where you have a pin or a roller or a free end, because there's nothing there that can support a moment. And likewise, you're going to have a triangle section here. So this is 40. This is 0. You're going to have 40. And over here, it's also going to be 40. So you're going to have 40 here and 40 here. So you're just going to connect these 2 points. So you should have a trapezoid here. I didn't draw it very well, but you should end up with a trapezoid section here where this is 40 and this is 40. This is 102.8 and this is 102.8. Okay, so we have that, and now we need to draw our Q system. So I think so far we haven't really done anything unusual. Everything has been pretty normal, but very interesting things happen. And I didn't realize this until the professor told me why. Let's find delta AX first. So to find delta AX, we're going to apply a unit load of 1 at AX, at A in the X direction. And we're going to see what our forces that develop. So I am not going to go into how to get the reactions for this. I will just say that you will have an axial component in here, and it is not necessarily what you'd expect. For example, the vertical reaction right here is going to be 0. And you might say, well, how do you have a vertical reaction here and a horizontal reaction here and an axial force in here that results in a vertical force of 0? You see what I mean? So your axial force that develops in here is going to be 0.6. Your axial force that develops in here is going to be, sorry, let me write this up here. It's going to be 0.6, and this is going to be in tension. And you're going to have 1 axial force in here, which is also tension, and you're going to have 0 axial force in here. You might be asking, well, how is AY 0? I'll tell you that AY is 0, but it might be very odd to you that you can have an axial force in here and a zero reaction in this direction, right? Because 0.6 times cosine of what is this, 38 point something degrees is definitely gonna be equal to 1, and then cosine of something or sine of something should be equal to 0. There's nothing there that would make sense. And it turns out that because this is a frame, you also have shear in here, and that shear is what is gonna cause your axial force, and that shear is what is why your vertical reaction here is 0. So I will say, don't forget effects of shear. Or I will say, not don't forget, but note shear. Okay, so that is fine. Again, I'm not going to go into how to derive the moment equations, but I will just tell you what they are for the sake of this problem. You have, this is going to go out to -4. Likewise, you're going to have a rectangle up here, which is -4 and -4. You're going to have another triangle over here. Sorry, let me make everything negative. I think everything should be negative. The sign does not end up mattering, but because everything cancels out, I just want to include them now for the sake of consistency. Okay, so we have this. Now let's get into our equations. The moment equation we have for the moment equation, or the work method I'm going to use is the over EI. This is area times centroid to apex of Q. I think this is causing, I think the terms in here is causing some confusion. So I'm going to try and resolve that if I can. Let's look at section AB. AB. Let's draw the triangles again. So I'm going to draw these sideways. These are diagonal members, but I just want to illustrate some points. So this is P, this is Q, this is 102.8, and this is 4. This is negative, negative, negative. Yes, okay. Let me include the lengths here. This is length 5. Okay. So what I think is causing confusion is what MQ and L, sorry, where's my original sheet? What MQ and L represent. MQ is the value of your Q diagram at the maximum value of your Q triangle. So let me step back a little bit. You always want to use you want to divide your Q diagram into triangles. They don't have to be right triangles. They can be any shape you like. So I have a rectangle up here, and this looks like a parabola, but this is actually a diagonal, a straight line. And I want to divide into 2 triangles. I have a rectangle, I divide into 2 triangles. I only need to do this for my Q diagram. I only need to split the Q diagram into triangles. The P diagram can stay as fine as it is. Okay. So the MQ is the maximum value of this the triangle you're looking at. The L is the length of the triangle. So for this case, let me use a different color. My MQ is going to be 4. My L is going to be 5, because my L is the length of this triangle. My MQ is the maximum value of my Q diagram. And note these two triangles are right here. I just pulled these out. I'm ignoring axial forces for now. I included them here just for notation's sake, but you'll find that their axial forces are negligible in our problem. But it's this triangle and this triangle. I just pulled them out here. Now the area of this triangle, if we do the Presser's notation, which is MP over EI, is going to be negative 102.8 times 5 divided by 2 over EI. And the centroid is going to be, now the centroid is from the apex or the tip of your Q triangle. And what is the tip? The tip is wherever your Q diagram is 0. So the distance from this point to this point. And that is just going to be 2/3 times 5, because we have a good triangle up here. So yes, you just need to multiply all of these things out, and I believe you should end up getting 685.3 over EI, I believe. So this is negative 4 divided by 5 times negative 102.8 times 5 divided by 2 EI times 2/3 times 5, and that should be 685.3 over EI. The next part is your middle section, and I think the middle section is going to be the one that most of you had trouble with. This is where we have the trapezoidal section. So let me draw that again. Let me draw this using green. Let me use green for the moment diagrams. We'll save black for the axial diagrams or something. So here we have this is 102.8, and it goes down to 40. And then our diagram over here is, and this is just a rectangle. Okay, so our Q diagram is a rectangle, so we need to break it up into two parts here. And this is negative 40. Our L here is length 4. L equals 4. So when I split this up, let's see what happens here. My MQ diagram is going to be, or my MQ value, let's look at triangle 1 and triangle 2. For triangle 1, my MQ is negative 4. My L is equal to 4. The area of my trapezoid is going to be negative 40 minus 102.8 divided by 2 times 4. The area of a trapezoid is always average of the bases times the height. So this is negative 40 plus negative 102.8 divided by 2. That's the average of the two bases times the height. And recall that the bases are the parallel sides. And this is all over EI. And now the centroid. The centroid is the interesting one. For centroid, I'm going to divide this up into two parts here. And I'm going to call this A. I'm going to use X bar. This is how I find the centroid. I draw my little shape, and I'm going to call from here X. So I want to find the centroid of this trapezoid with respect to this side. So what is that? What is the area of this rectangle? The area is I'm just gonna use positive values here. Is going to be 4 times 40, which is 160. what is the centroid of this triangle? Centroid is just L over 2, so it's 2. And then the product of these two things is 320. Now my triangle, the area of my triangle, this is 102.8 minus, this is 40, and this is 102.8 minus 40. So this is 62.8 times 4 divided by 2. So the area of my triangle ends up becoming 125.6. My x bar is 2/3 times 4, which happens to be 4/3. Sorry, that doesn't sound right. Sorry, my x bar is 1/3 times 4, which happens to be 4/3, which is 1.33. And my ax bar is 167.5. My ax bar is just this column times this column. And if I add all these things up, if I add my area, I end up getting 285.6. If I add my ax bars, I end up getting 487.5. And now if I say ax bar equals A, so my x bar is equal to 487.5 divided by 285.6 is equal to 1.707. This was just to find the centroid of this whole thing up here. And I need that for here. What is the distance of the centroid of centroid of this trapezoid to the apex of 1? Well, the centroid is here. This is 1.707. So this must be 4 minus 1.707. And so my centroid distance is 4 minus 1.707. If I look at triangle 2, my MQ is equal to -4, my L is equal to 4, my MP is the same, and the centroid is 1.707. Now you might have noticed, well, these two things are the same. So if I subtract 1.707 times all of this, and I add 1.707 times all of this, then these two things should just cancel out. So my for this whole region, whenever you have a rectangle here, you don't have to worry about the centroid. Or I should say you don't have to worry. The centroids end up canceling out. And I see that my battery is almost dead, so I'm gonna stop talking for now. But yes, the value in here is going to be, you should end up getting, for this whole section, your MQ/MP over LEI to be 1142 over EI. Okay, and then I'll upload the rest of this later. Actually, I don't know how much more I need to upload for this one because the solutions are available for this. And I think this part was a tricky part. So if you're able to get this part, you should be able to get any type of problem that you have. So yeah, let me know with your questions. If enough people need it, I will finish this problem, but I think that this should be enough to work you through virtual work.